All right, today we're going to pull back the curtain on this tiny, pretty much invisible marvel that powers our entire digital world. You can't see it, you can't touch it, but it is the engine of, well, pretty much everything, the microprocessor.
Okay, let's just dive right in. I want you to think about one piece of technology. It's in your phone, it's in your computer, your car, maybe even your coffee maker. It's something you are using right now, but it's so incredibly small, you'd need a powerful microscope just to catch a glimpse of it. So to really understand this hidden engine, we first need to kind of zoom out and look at the big picture. The basic anatomy of any computer. Look, every single computer, whether it's a giant server in a data center or that smartwatch on your wrist, it's got these four core parts working together. You've got your input unit. That's how you tell it what to do. The output unit, so you can see the results. The memory unit, which holds on to all the information. And then the star of our show, the central processing unit, or CPU. And this is absolutely the key takeaway. The CPU, it's the heart, it's the nerve center, it's the brain of the whole operation. It's the part that's actually doing the thinking, fetching instructions, crunching the numbers, and telling everything else what to do. Okay, so now let's zoom in on that brain. It's time to finally meet the hero of our story. So what is a microprocessor? Well, simply put, it's what you get when you take that entire complex CPU and you shrink it and shrink it and shrink it down onto one single tiny chip of silicon. The whole brain of the computer right there on one little integrated circuit. Now, it's super easy to get these terms mixed up, so this little table should help clear things up. The microprocessor is just the brain. A microcomputer, think of your laptop or your PC, that's a complete system that uses that brain. And then you have a microcontroller, which is kind of like a specialized all-in-one chip designed for one specific job, like running your washing machine. So just how micro are we actually talking about here? I have to tell you, the scale of this technology is, well, it's genuinely hard to wrap your head around. Okay, get this. Our source material gives us this absolutely stunning comparison. Just let this sink in for a second. If you pluck a single hair from your head, it is more than 2,000 times wider than a single transistor on a modern microprocessor. To put a number on it, one of these fundamental building blocks is just 0.045 millionths of a meter wide. I mean, for comparison, that's smaller than most viruses. The engineering required to build things at this scale is just, it's astounding. So this incredible ability to miniaturize things kicked off this unprecedented race for more and more power. A great acceleration that started all the way back in 1971. You can really break down the history of the microprocessor into these four distinct generations. And the key thing to look at here is the bit size. Think of it like a highway, right? A 4-bit chip is a narrow little country lane. It can only handle tiny chunks of data at a time. The 16 and 32-bit processors of the 80s, well, those were wider highways. They could process way more data at once, and that's what made the first personal computers possible. And then, from 1990 on, we hit the 64-bit superhighway era, where transistor counts just exploded into the millions and now billions. And this incredible pace wasn't just random luck. It was famously predicted by Gordon Moore, one of the co-founders of Intel. His observation, which we now call Moore's Law, basically said that the number of transistors we could cram onto a chip would roughly double every 2 years. And for decades, he was astonishingly right. Now, that pace is slowing down today because we're bumping up against the laws of physics, but this one idea defined the entire digital revolution for half a century. So let's see how this actually played out. It all started right here, with the Intel 4004. With just 2,300 transistors, it was this revolutionary little chip that powered calculators. But just look at the jump to the 8080 only 3 years later. It was over 10 times faster. That became the brain for some of the very first home computers. And then came the 16-bit era, which brought computing into our offices. The Intel 8286 you see here, that was the heart of the iconic IBM PC/AT. With 134,000 transistors, it had enough power to make the PC the undisputed king of business, running spreadsheets and word processors. Okay, and this is where the modern age truly kicks off. With the 32-bit 8486 back in 1989, we crossed that magical 1 million transistor mark for the very first time. I mean, that's a huge milestone.
This leap in power is what made graphical interfaces, with windows and icons and a mouse, possible. And then came the Pentium in '93 with over 3 million transistors, and the game was changed forever. But here's a really crucial point. This explosive growth couldn't last forever just by shrinking transistors. As these chips got denser, they got way hotter. So to keep this incredible pace going, engineers had to get clever. They had to develop these brilliant architectural tricks to make processors work smarter, not just faster. And this was a totally revolutionary shift. And really, two key strategies came out of this. First, they built much smarter memory systems. And second, they figured out how to make the processor do more than one thing at the exact same time. Okay, first up, memory. A CPU is incredibly fast, but the main system memory, it's comparatively slow. It's a bottleneck. So to solve this, engineers built caches, these small, lightning-fast pools of memory right on the chip. It's like having a little notepad right next to you, instead of having to run to the library for every fact. They even built caches for the caches and developed smart tricks like prefetching, where the system actually guesses what data the CPU will need next and gets it ready ahead of time. And the second brilliant trick was something called instruction-level parallelism. So instead of making the CPU handle instructions one by one, like a single-file line, engineers figured out how to make it overlap tasks and execute multiple instructions in every single clock cycle. It is literally the difference between a one-lane road and a multi-lane superhighway.
So, after 50 years of this relentless innovation, of Moore's Law pushing us forward, what does all this mean for you right now, today?
Well, it means that the device that's probably in your pocket right now has an incomprehensible amount of power compared to the machine that started it all. We've gone from 2,300 transistors to over 1 billion. We've gone from clock speeds measured in thousands of cycles per second to billions. The result is that you are walking around with a pocket-sized supercomputer that would have been pure science fiction just a few decades ago. This incredible journey of exponential growth has literally defined our modern world. And now, with Moore's Law starting to slow down, it leaves us with one final, fascinating question to think about. If just shrinking things down drove the first 50 years, what new kind of innovation, what new brilliant idea is going to drive the next 50?